Hi, everybody. Welcome to one of our Stewart lecture series on AI. This is our first hybrid one where we have people in person and online. And so I appreciate everyone coming in today and everyone online showing up. Today we have Dr. Zahid Hasan. He's a third-year PhD student. We invited him over today. He had an excellent paper about a device that can actually read your heart rate by visually looking at your eyes. He is working in a number of areas related to remote health monitoring with lots of low-cost video sensors and different methods to extract heart rate from these sensors. And so in particular with this lecture series being about wearable devices and heart rate monitoring and things like that, I thought it was very applicable to this work. I think it's also interesting from the wearables perspective, if you're kind of curious about that kind of data set and everything and kind of how the warfighter feels about it. There's a lot of bright green lights going off on your wrists and you have to wear a certain watch all the time. And there's been a lot of negative responses about that. So I thought in particular using image systems to gain data about a person's physiological state was of great interest. And Mr. Hasan's paper, it really highlighted that well. So without further ado, we'll have him take over and I'll just switch to sharing your presentation, sir.
So thank you, everyone. Thank you for the invitation. So this is a great opportunity for me personally and for our lab to showcase what we do, and hopefully it's a broader audience for our works. So today I'll present one of our recent work, the RhythmS, where we try to extract heart rate from.
Sir, thank you so much, pretty girl.
So this work has been collaborated with our lab mate Imonde, Srinivasan Ramaswamy Ramamurthy, Dr. Nimal Roy, and Dr. Archana Mishra. So, and this work has been supported by NSF, Dr. Professor Roy's NSF Career Grant and DEVCOM-ARL funding. So, okay, so with further ado, I'll go back to our topic. So, heart rate, as we know, like the typical how it beats per minute, or that's one of the first thing that doctors do when we go to hospital. They get our like heartbeat and pulse, how it is going. So it's a very important physiological parameter and primarily used parameters of like living and like dead people and how his like blood situation is. So the existing heart rate system is kind of I would like in a broad category. One is ECG. That's the most compelling heart rate device that like there is different leads that is placed to your bare skin, and from that they get a thorough heart examination. So however, the problem is imminent. So the issue is you need to be in clinical setup. So there is no way we should like replace the ECG. It's like extreme case, but it's not always mandatory that okay, I need to check my heartbeat, I need to like do ECG. That's not always. So ECG is a clinical setup. We need clinician, and it is still the most reliable heart parameter, heart examination. It not only gets the heart rate, but also all this other stuff, the PQ peaks, how the heart beating is, like all this synthetic and parasympathetic works. And another line of work that we every day see, like our Apple Watch and the other wearables, they actually calls photoplethysmography signal. So what that does, they measures our volumetric blood skin volume from our peripheral body. So what happens when our heart pumps the blood, our peripheral gets the blood volume boost up, and when the heart again pulls those blood, it peripheral skin blood gets like a volume decreases. So if we can measure this peripheral volumetric blood, then we can actually trace back how's our heart performing. So this is synchronous to the blood volumetric variation is synchronous to our heart activity. And there is like two major lines of research wearable devices like Apple or like PPG sensors. We see them in medical use when we sometimes go, they put a like clip on the fingernail and they get the heart rate. And another line of interesting work that has been firstly discovered by Valkyries in 2018, that we can also measure heart rate without contact setup. So those wearable sensors requires contact, and they are requires close contact and proximity, and it's sometimes not always convenient to like remove my cloak and watch and like make others wear and then measure the heart rate. So the remote PPG actually tackles that problem. So it tries to estimate PPG or like photoplethysmography or BVV, the volumetric blood variation, via a video sensor. So the first thing is like, is it even feasible? How the heck going on? So for that, okay. So my talk will be overview of the what's the PPG physics is. Is it like physically doable, and how we are doing it? And then I will follow up with our contribution, our system approach, and what types of challenge we faced, and finally we'll conclude our work with some future work direction and some of the works that also I'm interested in and kindly pursuing. So firstly, the PPG, the remote RPPG physics. So what happens in light, the camera captures, when the camera captures our face or like our face. So there is the fundamental idea is there is two types of light that is reflecting from our skin. The first one is speculative signal. That is the everyday signal. Like you can watch me, I'm watching you. This is the speculative signal. So we just see what's going on. And the other thing is the diffusion signal. So that's our signal of interest. So diffusion signal. So you can see the first picture that light goes into our skin and it like penetrates off our skin and it reflected back from our body again. So you can see. Okay. So whenever there is like a blood vessel, there's lower amount of blood, the diffusion reflection is really strong. And when there is like a higher blood volume, then the diffusion signal is small because light absorbed by blood. So as the blood is high volume on your on our skin, then reflected light is low. And when blood is of low volume, then the reflected light is strong. So if we can somehow track this diffusion signal, then we actually have the PVV, that means the volumetric blood variation of our skin. That means we can track back how is our heart performing. So that's the fundamental idea of RPPG system, that we need to capture the diffusion signal, not the speculative signal. So yeah, so if we can like go pictorially, let's assume this is a like face and there is very low blood volume. So we get a reflected diffusion signal. With the progression of time, some blood came, then the signal diffusion reflection we get weakened. Then if we continue this way, we can see whenever our heart pumps the blood to our faces, then the reflected signal goes below again. Again, when the heart pulls up those blood, the reflected signal goes up. So if we can somehow develop a system that successfully captures this volumetric blood variation, that's our RPPG system. So our research work actually focuses on that. And this RPPG signal is in the spatiotemporal region of the video. So the idea is clear that we need video because in one image, this just get one reflection that does not give away the whole time series data. So we need a series of phase and see how the heart rate works. Like what doctors they do, they like captures them and then like count for 1 minute at how many times the heart like the pulse beaten. So the idea is similar here, that we need temporal phases with this diffusion reflection. So all we need a new some types of model or some types of black box, I would say, to capture this, to extract this diffusion signal that will eventually give the heart rate. So that's the idea, that that's the diffusion signal we need to figure out from the okay. Again, so the motivation of RPPG is that it's like ubiquitous heart rate monitoring system. So firstly, it does not require any contactless sensor. So we can capture this using our even cell phone cameras if the camera is somewhat good. So I'll come to that point. So it's an easy to monitor system, and again requires no skin contact. So that's always good. And of course, it gives a better safety. As we know, sometimes contagious disease may happen. Like some skin, sometimes our skin may may affect on this wearable. So this video-based sensors actually eliminates all those problems. So the issue is regularly used. So if this is so good, and using them regularly, why I'm probably have not heard of it, but don't see these devices very regularly, right? So there's the three issues we figured out that are limiting these applications. Firstly, the signal that we have been talking about, the diffusion signal, you can see most of the signals are speculative signals. So diffusion signal is very noisy signal. So we need robust system to first capture this diffusion signal. That if I'm using very bad camera, it might not capture the diffusion signal. It's just so that can happen. So firstly, request to robust model to estimate that heart rate or BBB from the face or any video. So the model is not well placed. So the model is an issue. Second thing is that expensive video processing and competition. The video processing is always one of the most memory competition device. So sometimes our mobile and other things, we do not want to put any video processing there because video processing actually slows down everything. So that might not be a good idea. And finally, that this RPPG has not been explored in edge devices like Jetson Nano and other edge devices that we regularly see in our most of these robots and other things. So they have not been. RPPG had not been explored how they match with this edge device and the other settings. So that's again one of the drawbacks that so far in our research we will be trying to address and bridge the gap. So our whole objective of this research is to develop a low computational, ubiquitous, reliable, stable RPPG system for monitoring heart rate continually using off-the-shelf video camera. So yeah, low efficient, we would say that we want some model or some computation approach that does not require a lot of memory, that does not require a lot of power, so that our device does not get overheated. Secondly, ubiquitous. We want to have regularly used device like our web cameras, like our mobile cameras, like maybe action cameras, like GoPro cameras, or maybe those regular cameras, so that we don't have to again buy some very sophisticated cameras. So that's our ubiquitous goal. And finally, reliably, since we are dealing with heart data, we do not want to give any wrong impression that it's always showing, oh, your heart is good, but maybe that's not true. So we do not want to infer any wrong information, and there is ethical concern with that. I build a model that always says that your heart is good or your heart is bad. So this is not how it should. So stable RPPG data, it requires to be stable in inference, and it also requires to be stable in device operation. That we do not want to overheat and destroy our device throughout the process. So that's our whole goal. We want to focus on low computation, ubiquitous, and reliable estimation of PPG signal using off-the-shelf cameras. So there's two types of challenge that involves, and we have addressed throughout our work. Firstly, the algorithmic challenge, that what type of model we are building or developing to extract heart rate from PPG signal. And how do we make these models very computational efficient, that takes the video input and tries to figure out what diffusion and how the diffusion signal is that. And of course, can we compress everything in very short computation device, and of course, finally facilitate stable RPPG device. And these are the algorithmic challenges, and there is also some engineering and system level challenges that firstly, we have to make sure that cameras contain the RPPG signal, that means the diffusion signal inside. So how we are gonna, since we are using off-the-shelf cameras, so how we are gonna integrate these cameras to regularly used devices. So also, can we facilitate video processing in these small edge devices like the robots or even our mobiles? And of course, the camera will be heterogeneous cameras because my mobile's cameras may be like smartphone, someone others maybe iPhone. So there's also device heterogeneous issues. Like GoPro camera has wide angles, meanwhile our mobile camera has flat angles. So these types of issues. And finally, we want to benchmark everything that since this is the first line of work, we want to like give a total picture of how it device in the works in the device, how's that device, or do that device over or has the memory issue or some other issues. So we want to benchmark. We wanted to have a benchmarking of our system performance. Okay, so yeah, so this is a typical PPG setup that we will have a cameras. The person will sit in front at least from 3 to 6 feet. In our case, I'll come to this point later. It will capture the videos and it will do some processing and finally give us the PPG signal. So we have to encapsulate everything, the blue section in small devices. And there is also challenges like does the camera is capable of capturing RPPG data in the first place. Okay, so to our end, we contributed particularly 3 things in our throughout this research. So first, we have developed a compressed RPPG model. That means the resource efficient, stable RPPG model that can tell our heart rate from video data if the video is captured in some good setting or like stable setting. Secondly, we developed the system and prototype our approach that it not only works on like computer, it also works on edge devices. We actually have three different like one of the most ubiquitous device that like our system works on just on Nano. We developed our system for Google Coral Dev Board, and also we developed our system for our Raspberry Pi to show that it's not like device independent, to scalability of our system. And we also facilitated both real-time and offline PPG systems. So the real-time will sit in front of the cameras and it will give us the PPG. And offline means I have some video data. I can send this data to the model for the existence of model. It can get this video and give the corresponding PPG signal, eventually the heart rate. And we of course like validate our system for by metrics like what the accuracy we are getting, how's the memory, time complexity, and since these are small device, the power is also important. We do not want to overheat by doing some video processing for heart rate. So this is another concern while developing these approaches. So our RPPG system works. Firstly, it requires a stable person. That means the person requires to be sit in front of a HD cameras, and HD cameras is all the systems. HD cameras is very regular, even our mobile and most of the laptops. Web camera is kind of HD supported, so the camera requires to be face focused, and the person requires to only sit in front of it for like 30 to 40 seconds in a stable position, or the way we are sitting right now. Even the way I'm standing, it should be fine because this is just like regular movement. I'm not doing any rigorous movement. So that is what stable camera person setup. And it requires camera like at 30 fps, and ideally most of the cameras is 30 fps. So that is also like within standard. And so after getting the video, video by stable camera person setup or this HD camera, it will send this data to some edge devices, for our case Raspberry Pi or Jetson Nano, either via wired connection or via cloud connection. So we can, in our platform, we used both Google Share and also GitHub platform to send the data to the device itself. So, and wired connection is always like real time. It's just connected by wire. And finally, it will from this video, it will estimate how the BPV signal, the volume of my facial blood is moving. So that's our goal. And we also we have a like little engineering that we can store and send this data to the user. If they provide their email, they can instantly send their heart rate to the user image. So that is also another feature. Okay, so the first thing that is while developing and my research work, that to develop a baseline model. So how do we develop a model that can extract heart rate from raw video data? So that's our first approach, and in that work we actually developed a convolutional neural network based model to develop a model that can extract PPG from video data. So for that, we also collected our own data set, because the RPPG, again, we discussed that this is not like well established data set. So we put one of the now our data set is in the most on top of like RGB data set. So it is one of the highest amount of data we provided. So it is also in open source. You can look into our data set. So we collected our RPPG data and of course train and validate our models with those data, and also public data set I'll show. So my first research question was how to develop a baseline RPPG model. So for that we actually published and got good results and validated our result and published one paper called CAMSense. That is a multitask-based solution to this RPPG models. So this model, we had to like do some address some of the challenges, like how do we avoid ground truth misalignment, and how do we annotate all these types of data, and how do we learn from this data. So that is my first research during that I did when I started my PhD journey. So that is the first work we have done. And the second work we have done also self-supervised baseline model. So this is another work that I have done, and it has been accepted in chess, but it is not in proceeding yet. Hopefully it will be there soon. So we actually address that how if we can develop RPPG video data without requiring any level. So we actually proposed a physics-based method that can extract the video diffusion signal without requiring any level. So that's our second baseline model approach. I'll not go into details of that, but I can definitely discuss if somebody is interested that how will you do that and what's that. So for that, we'll take granted that okay, using this approach we can build a model that actually can extract heart rate from video data. Now, if we have that model, but normally these models are really heavy. It works on raw video data, so the model size is itself 2 GB. So it does not work in regular small devices, and even my GPU computer has like some issue of running them. So this is not straightforward. Even if we have the model, we cannot just take the model and run into some small devices. It will not have work. So our hypothesis is that we can compress this model somehow, and there is some like there is different compression mechanism. We can take some advantage of these approaches and compress the model. So the idea of compression is that your model size should be reduced, but your accuracy needs to be like retained, like the big model itself. So that's our model compression hypothesis, model compression approach. And since we utilized another information of this RPPG specific information, that the RPPG is a phase information. That means even there is like the video is capturing all those background, that real RPPG exists in my face. So that's the idea, that all the video does not require to be like considered to capture the RPPG information. And we have looked into that and found that the normally CNN layer captured this facial information, and the model is developed normally. You will see a CNN layer and there is fully connected layers. So we assume that if we drop some of the fully connected layer after developing, so we need to develop it fast because we need a big learner to learn everything. Then we can shrink down the problem. So we cannot just like use a small learner in the first place. That is also not the norm. So we need a big learner, and the compression idea is we can use that big learner to make it compressive so that it can be used for edge devices. And since we know what information we are looking for, the facial information and the backgrounds are kind of blurry, and the PPG is kind of periodic signal. So if we have the gist, we can kind of like interpolate between those points. So we can actually drop the FC layer is a kind of interpolation. So we can drop some of this FC layer, fully connected layer. So that's our ideas. And based on this idea, we explored weight pruning approach to shrink down our models so that it can be both used in small devices for memory and power consumption. Also work reliably. We do not want to like comprehend the accuracy too much to doing this pruning. So after pruning, we used model pruning approach to drop some of the unrequired words to facilitate the model to be generalized in low competition devices. So we prune the model, and of course we validated this approach in our public and our open data set. So finally, we also experiment with quantizations that how much do we require the high bit precision or low bit precision. 64, and turns out that PPG is again slow moving signal. We do not need the high frequency and very high points of that. So it also works with 32 and 16 bits. So we have figured out that it can also work with 16 bits operation. So by doing 16-bit operation, we can also like drastically reduce all the other weight compression and video compression. So it works on 16-bit compression. We also perform this quantization. So our model compression covers two parts. Firstly, it pulls the unwanted levels. Secondly, it really compresses the data in a so that it still can be PPG can be extracted without increasing any computational burden. And then the engineering challenge, we had to like fit everything there in small devices and transfer this edge model, because each device is like they have their mind of their own. So we need to like change our approach for each of these devices. But our goal was to demonstrate that it can be like scalable for different devices. So yeah. After we put this in edge devices, now we require only the video. That's it. So after all this development approach, we'll get the video. It will do some pre-processing to get the video. For our case, we take 40 frames, and the 40 frame is calculated for a good reason, because our heart rate is about like 72. So for like at 1 second, we get a full cycle. So that's the idea. So if it is like 72 cycle in 1 minute, so at 1 second we expect at least get a full cycle. And sometimes if the heart rate is like more like 140, then we can get 2 cycles. So that is still good. So that's our motivation for selecting 40 frames. It actually covers 1.33 seconds. So we try to extract 1 cycle per second or 1 cycle per computation. So that's the idea. And again, the idea is like since we are selecting 40 frames in 30 FPS, 40 frames means 1.33 seconds. So the model will work only after 1.33 seconds, and it gives a good like breathing space for the model. So since the video is coming, so 1.33 seconds, it got some video. It tries to extract the video inside this 1.33 seconds, and by the next 1.33 seconds, it will get another frame, and like it will continuously extract the model. So the 40 frame is a design choice and engineering selection to facilitate these operations inside these edge devices. Again, there is some like technical challenges we faced. How do we like set up everything that does it work? We are developing the models in GPU-based computer. How do we convert these models and apply it in GPU-based system? And finally, after extracting heart rate, we actually send this result and PPG to the big GPUs where we can further analyze the PPG, how the P to Q distance or the R to R peaks. Did we get any like anomalies in the BPV? Is it the signals fault or is the person who's like is the subject who's under radar? He has an issue with that. So we further further analysis, we send this to edge devices, and it allows us. We actually have a tabular setup. Again, these are the engineering solution we have provided that it saves the longitudinal data that okay, like in May 4th, I have the heart rate of that. In May 10th, I have the heart rate of that. Is there any anomalies or this is the regular? So we also facilitate this longitudinal data storage for the subject who's like inside it. And finally, we have performed experiment with our own data set, the MPSC data set, and the way why we focused on that because this is the like for now, as per my knowledge, our data set is the largest. There is other two public data set that is available, the MAR, the Mitsubishi Electrical Research Laboratory data RPPG data set. So their data set is has like other modalities, but we focused on RGB because the availability of the RPPG because these are most common sensors. And finally, the UBFC dataset. This is the dataset from university. I forgot the university. It's still like the university is in France, so they have a dataset. So to my knowledge, these are the like more the vast three dataset available currently for RPPG research. So ours are good in RGB, but we don't have like other like infrared and other things. So they have like other applications, but we mostly focused on the availability and ubiquitous approach. So that's why RGB makes better sense because these are most available sensors. And finally, we implemented our devices in three setups there. Hasan Nano, Google Coral Dev Board, Raspberry Pi. Also, we worked with three types of cameras, so web cameras, action cameras, and also DSLR cameras. So it works with that. So, and the web camera we selected is pretty close to mobile cameras and other computer cameras. So it's equivalent to those like mobile computer, most of the computer web cameras and mobile cameras. So. And finally, we provide our software stack, that every code, every process, every software requirement. This is you can see in the link. So these links provide every instruction that what type of problem you will be facing and how to probably get out of them. So every instruction and how to like manage. We open source everything to like encourage any further research and development. So our codes and data sets are even the instruction and device setup are all available in the web page that we have done. I'm not sure there should be a video, but it's not.
Like earlier.
Yeah. So yeah, I used to we could show how the prototype looks. It's like a normal camera and small device. So yeah, there should be a video on it work.
Yeah, you can try to stop sharing it and see if it pops up.
It's flatline. I think we can show it later. It's fine. Okay. So yeah, like yeah, in that device we also have memory and power devices that continuously monitor power. So this memory and power is only for the development purpose. We do not, since developing, we do not want to like make the system unstable and make device overheating. That's a common issue while working with the video data. Oh, it works. My
It's the slow government internet.
So yeah, you can see the cameras. Those are that are the devices. So the person is like working on his laptop, does not minding what's going on. So it will give us the camera values and it will finally send us the heart rate once in like 30 seconds because it requires to be like a bit heart rate. We cannot just calculate in 1 second. It takes like it's a temporal signal and the beat is going on. So although like 30 seconds maybe too much because we have also option to just send the heart rate after 1 minute of calculation. So once we get the PPG, there is like frequency domain transform and the signal is quite clean. So we just take our frequency of interest, because we know heart rate is normally from 1 hertz to 4 hertz. So we take that frequency band and capture what's the most dominant frequency term. Yeah, so that's our so again, these are the device and other things. Now we actually like computed our device on time, memory, and power consumption. And these are the some of the pictorial PPG estimations. So the green one is the ground truth that is captured by wearables in ear wearables and other finger like hand wearables. So these are all on test data set. So there is no monkey business there. So yeah, and our model can estimate PPG quite on par of the variable signals. So we can see some high frequency component, but like I discussed, the high frequency does not bother our final heart rate estimation, because our heart rate is normally 1 to 4 hertz. That's a very low frequency, but this zigzag will be on high frequency. So we can use a normal low pass signal or like band pass signal to get rid of those unnecessary signals or like unwanted noises. So those are not in our domain of interest. If that would be in our domain of interest, then there would be like problems. And we also perform some statistical analysis, shows that our model is doing very good. So the we can see some PDFs. We can see if the PDFs are aligned close to 1. We can say our model is. These are some evaluation metrics to show our model is statistically performing really good in terms of the result is giving it statistically significant. We are not interpreting some garbage values. So these are some of the consistent. This demonstrates our consistent performance over the data set. So again, these are runtime analysis purpose. So we see how the model is actually taking the times and to pre-process all these videos and how it is doing everything. So we can see from the OpenCV part, that is on the like video, it takes video. So OpenCV has nothing to do with our work, but we can see our model is really fast in we can 0. It interfered in 0.33 second, and we inferred our result for 21 second whole as a whole. So on the 1.1 second is good, because we have again 21 second of breathing space between next processing. So yeah, for now we are using frame by frame processing. So we got some interesting feedback that why you are using frame by frame analysis. You can also parallel those frame operation, because the frames are like you don't need to work on frame by frame. So that's another future work that we want to like do the serial operation. Can we go beyond by making these frame parallel operations? And we also show that our memory is in par with the devices, that the devices we are working with does not like go overboard with the memory, and it also does not hamper their other operations. For example, JSON Nano was deployed to capture some of the like real-time videos. So if we run this on top, will it like stop those videos? So we figure in our experiment we showed that it does not like hamper other operation. It can consistently do its other work, like the line following and the other thing. Meanwhile, it can operate that, and it requires a like really low memory even for them. But whenever we tried our big model without compression, it was a disaster. So it did not work that way. So after compression, now we are within the memory bottleneck problem. So now our system works and it does not hamper the device like RPPG and the Raspberry Pi and the other devices regular workflow. So that's a positive for us after. Although there is some like internal issues that JSON requires higher memories, Google Coral require lower memories because the architecture and the other things, how the devices are built on. So. And we also like again the QC quantized 16 should be the best, and we found that okay, it's the most memory efficient with a little loss in accuracy. Okay, so and again, we not only work with like 30 FPS cameras, we also have tried the things with higher FPS because the slow motion cameras and other cameras. So the idea is they works, but previously we are having only issues with 30 FPS. That means 30 frame per second. Now we are just dealing with 120 FPS. So that the memory issue is with the device. The device like it just computation got 4 times complex and it actually does not work for 120 FPS. And some of the even devices it does not work with 120 FPS. So this is a feasibility study, although like most of our cameras, our regular cameras are 30 FPS, but since the device is picking up like slow motion and other, can we go beyond like see even beyond how like these things are work. So we performed the feasibility studies on the other tools. So 120 FPS did not work is because of the memory bottleneck. Hopefully, within time, the NVIDIA guys make a better device that can facilitate 120 FPS video operation. Until that time, we are good with like 30 FPS operation. And we also perform like why only fully connected layers? Can we perform CNN layers too, right? So we demonstrated that like after performing CNN layer, the model compression like model size is like bit lower, but the error graphs goes high. So we found that okay, we better not touch the CNN layer. So with the gain is low. We are compressing very little, but accuracy is dropping significantly. So we did not pursue any of that again, but there is another like there is some research line that work on CNN compression. Maybe that can be a future work that how can we even compress our models. And finally, like how when our device works and when our does not work. So the first thing is that the camera requires to capture the diffusion signal, right? If it does not have diffusion signal, we cannot infer anything because this is a like simple limitation. I don't know what's beyond the room because I cannot see it. So that is how it should. So if there is no signal, we do not want to we do not want to like estimate any RPPC. If only there is a signal, then we want to estimate. Okay, now there is RPPC signal. So that's our point. So yeah. For the videos we works, 3 to 6 feet distant work pretty well. And again, you can see that the distance will be depending on the sensor. If we use a high powerful sensor, it can capture this low diffusion signal from beyond. But if the camera sensor is bad, then it might require to come close to capture this diffusion signal. And the relative motion is the issue. Still, if I move like vigorously, like significantly, then the model fails because the diffusion signal is already low and now I'm putting an extra noise, so it does not work. But most of our case, our point of like discussion is that like even in the clinical setup, doctors would like breathe and like make your hand steady. So that's the issue. So the idea is if we move very fast, there is no diffusion signal, so there is nothing to infer. And the relative camera position for our experiment, we have shown that the camera does not require to be like straight in front to like it has to, you have to look into it. So even if it is some side, if it gets some facial portion, it still gives a significant result. And the sensor impact is a thing that what type of sensor we are using is a like important thing. And finally, the lighting, that the diffusion signal origin is the light, right? Because it goes into our face and then come back. So the lighting source, it should work best in monochromatic light when there's only one light source, one type of lambda and frequency to deal with. So artificial light works best. We also tried for sunlight, but direct sunlight did not help. But if there is a sunlight, but we are sitting like opposite of sun in some shady area, in some shade place, so that also works. So, but the issue is direct sunlight. Our model is still not capable of comprehending beyond the sunlight. And I hope this is the last slide. Oh yeah, this is the slide. So yeah, finally to wrap up our work. We actually demonstrated our RPVC device in 3 devices, and we proposed a new compression methods and we designed our models so that it can facilitate this RPPG technology inside ASS. Finally, to improve our work, we want to like parallel and other distillation method and other compression method we want to look into it. So that is our work covering RPPG, and you'll be glad to know that this work has won the best paper award in 2020 SmartCom that happened in Finland. So that's that is our work on RPPG. So yeah, I hope. Yeah, this is the last slide. I guess we have some time to discuss. Or...
Yeah, we'll do some questions.
15 minutes. So officially,
Yeah, you did good on the time. We'll do some questions from in here, and Mark, you can look to see if anyone raises their hand online. I'll open up with a question. I don't know if in your study, did you look at if like makeup or skin color or anything like that was impacting your ability to kind of?
That's a very interesting point you raised. So the data set we collected, we have 12 participants, and they have different skin tone of each of the. We selected the subjects from like athlete to their varying skin colors from various origins. So we performed this study from our laboratory setup. So there we have different person skin variation of like their origin variation. So it works on all of the skin, but makeup has an issue, and there is a paper corresponding to that. The idea is if there is makeup, the diffusion signal gets well low. So that's the issue. So yeah, it is not always if the makeup, it depends on how much makeup. If the makeup is really heavy, or even the mask, these are all like TSA stuff problem for that. But the idea is if somebody wants to shield the like the diffusion signal, then there is nothing. So if I wear a like big face mask or like wear sunglasses, then there is no diffusion signal to work with. So there's nothing.
Yeah.
So if the makeup really masks this diffusion signal, it blocks this diffusion signal, then there is no signal even to work with. That means we are working with audio and tries to figure out what happened. Like we are just watching it like random wall and tries to figure out what happened in thousands years ago. So that is, but that's a very good point. But yeah, I can refer to that point, that impact of makeup on art music. So people do this stuff. I don't know why.
If you want to fool with makeup.
Yeah. And there is like another work on that line. So they used a sunglass that actually reverts the that gives a random diffusion signal, because it's like sometimes scary that like we know that heart rate is sometimes used as biometric. I will use my heart rate to open some vault in something, right? So it gives your heart rate. That's scary that somebody has my video now, he probably has my heart rate. So Google has like opened a camera that gives a random diffusion signal. So you cannot like figure out the PPG for that.
So we're purposely trying to mask the diffusion signal.
So they just randomly give the signal of like radiate a signal of 80 hertz. 1.2 hertz. That means 80 bit per second. So now you say, oh, there is 80 bit per second. That's a very good heart rate. No, that's like much. That's like radiated by some glass. And if the radiation is stronger than the original diffusion signal, then that's what you will see. So yeah, there is some other research going on trying to defute it. That okay, no PPG for you.
Does anyone else have questions?
Oh, go ahead. So I saw you mentioned the inference engine you guys used for the compressed model was TensorFlow Lite. What led you to that decision?
That's a very good engineering question. So what that TensorFlow is like, again, Google, and Google owns everything. So Google owns these devices, and they said that TensorFlow TF-like model we will allow inference of this. So if you see some like model that is like small Raspberry Pi and other thing is inferring and doing object detection, so you can see that TensorFlow Lite is the underlying platform that they put some YOLO model and others. So we also wanted to go with TF-like model, so because this is more generalized and device compatible. So yeah, that's just like solution to the generalized or scalability problem. So yeah.
Great talk. I have a question about so since you're measuring this diffusion and it's based on the fact that if there's blood flow, the blood absorbs extra. So I imagine blood absorbs in a relatively narrow range. Have you ever tried playing with some sort of either physical or software level frequency filters so that you are dropping a lot of extra information, but only looking at a particular frequency range, and that way sort of maybe, lowering a lot of your data without actually losing anything? Or does that not work?
No, that's the exact, that's like a fast question, that why the heck do we need the AI model, right? So that is like, again, that is my fast answer, that can we use a normal signal processing algorithm, like making the like phase difference? So, and the idea is there is. So the first point I discussed that Becker is design, like first find out it exists in 2018. He used ICA model that I will take the video and find all these like videos, right? All these signals, right? So if I can get these signals, like all the signals in the video, then one of them is diffusion signal. So we just need to like do frequency filtering and the other thing to get the video. So there is optical flow based method, and this traditional method, it works with very constrained setup. So for example, if I give only skin cut, that means just one skin, I block it. Then if I figured it tries to measure intensity, then we can like use a normal filter of that. But the issue is like normally our cameras and mobiles, if we put it in front of our face, we don't get all the face, or we do not put it like really close to face. So there is many other background signal. My hair, there is some section where it does not have PPG, and all the skin. So traditional approach, the one that you've been talking. So we also have some baseline that before our, at least I think our research is like outcome results. We do not want to take any complicated steps until we have to. So we actually implied ICA based other frequency. There's many papers that are working on like this signal processing, pure signal processing approach, only take the model and do some frequency analysis. So they work with very limited setup. So they depends on the person's face. For example, some persons has like high PPG, some person has facial hair, some person has wears glass. So these types of variation, and every time we go to the IC and the other belt, and they also actually take this, they understand their limitations. So they work with mostly personalized setup. That if there is some like magnitude, how much do I have to multiply the signal? It can be different for me than you. So there is so much heuristic that even the Philips, like the guy who he works on the Philips, so they also avoided that. Now there is another guy who's called like Daniel McDuff. He did his PhD in MIT. So he actually showed that okay, CNN-based work outperform all of them. So, and this is the state of the art. And his work, and there is another work called Vitamon prior to our work. They also demonstrate that like this variation, like skin tone variations, background variation, normal signal processing methods face. But if we want to work with really close setup, that I'll be always on the white background, and there will be some person in the loop who will multiply the person's PPG. So I get low PPGs, I get high PPG, so I'll multiply it. And a normal signal frequency analysis will also do the job. But this guy is doing it, does it automatically. So it learns many things. So that's why it is a big 2 MB itself. It does lots of unnecessary things. It learns. And so, yeah. That's why our approach, I would say like, better in some like situation, but again, not better in every situation. So it's a contextual approach. Our approach works on like GPU context, like big models. So yeah. Thanks for the question. That's a very good question. That why don't we use normal frequency approach? We can, but there is some like obvious limitation. Yeah. So yeah, thanks for the question. That's a great question.
I could think of a gazillion applications for this, but I'm just wondering what you're envisioning, telehealth, lie detector camera, like what are you thinking?
That's a very good point. So my research work actually works on video understanding. So my whole goal was to like develop model. Of course, when you worked with, I started my PhD in like late 19, so just COVID hit. So we found, okay, what if we can use the contactless setup and the other thing? Even this video-based system can measure breathing rate. So my application is this types of, and breathing rate is important. When we get like excited, our breathing gets like unfrequency. And again, while the breathing counts, while the signal. So when you breathe, our like abdomen gets flat and our head gets split up. When we like exhale, our head gets like bit low. Although it's very low, if we like sit around, we'll see our shoulder is going up and down. If we can measure this shoulder up and down, we can also find the breathing rate. So yeah, so breathing rate is kind of easier because like the signal is more of obvious than diffusion signal. And that is on the speculation part. So my goal was to see if we can use this artificial intelligence to do this very exclusive video processing approach. And our whole overall objective is that can we use that to monitor some our situation, like we are studying and sometimes we get like frustrated when we are interviewing. If things allow us, like there is other privacy issue, if everything is considered, that we can measure how he's like reacting to some, like if there is like his heart rate suddenly got increased. And even in the medical setup, we do not always want to like put multiple devices. Even there is the infant monitoring system. I had an opportunity to look into that. So and they use infrared to measure the heart rate without like touching the baby body. So yeah, this is the application. Even in like in our home, we don't have IR camera. If this system really gets through lots of stable situations, then we can use our mobile and to check out the baby monitor, because baby's skin is too, like soft. So there's diffusion signal is way better than us. So yeah, so it can also used in baby monitoring and that. So yeah, the application domain is more of a contactless setup, but I mostly work with like developing like a video processing. My expertise on video processing domain. Yeah, that's a great question. Like every time I ask what I'm doing here, that gives some like I'd say like low breath. That's not my breathing. Okay, I'm doing something.
I think you said you had used Python for code. How easy was it to port between all the different devices?
That's a great question. So firstly, we have selected the devices because of their different architectures and their availability. So to go into the devices, each devices has like own requirement. So although they work in all over the Linux shell, but each Linux version is different. For example, Google Coral DevBoard has their own operating system. Raspberry Pi works on Raspberry Pi, and the Jetson Nano has their own operating system. So, however, they offer common TensorFlow Lite system. So some other guys are helping us on that. I don't know them, but they are working on to generalize this platform. So we did not have to change that many, but for Jetson Nano we have to change some bit, because Jetson Nano is like really different from Google setup. So, but the changing was more of a like trial and error, like restarting multiple time, doing bunch of code lines. So those are like hard stuff instead of, I'd say, like research work. So we had to work on like try different solution. One solution did not work, go over multiple Stack Overflow pages, and one of them worked, and we actually noted it what worked. So hopefully somebody else who will be working later than us will find this solution later. So we have all those solutions in this link. So what software package we used, because even software change, like other application does not work. So we tried to and I think our interesting thing was that we want to do reproducible work, that only I do it and like boom, like I can do it. No, we want some reproducibility in that. Yeah.
Thank you.
Great. Do you see anyone raising their hand on
I
online?
don't,
I love hybrid environment.
Do not wait.
no hands raised, nothing in chat, so
Awesome. One more question if anyone has it here, otherwise
we
we can.
wanna close out,
Yeah.
the recording?
Oh, yeah.
I mean, so they can hear you.
Gotcha, yeah. Yeah, so I'll just close.
Yeah.
Thank you so much for your
Thank you.
time. Really
And again,
appreciate
thank you
having
for
you.
your joining. That's great.
We really appreciate you coming over. It was a great talk. And thank you everyone for joining online. We're gonna wrap it up here.